All right. All right. So today we are moving forward in stoichiometry. We are going to do what's called limiting versus excess reactant today. We're also going to be calculating what's percent yield. So we're going to be looking at a couple of different things. Some new terms that we will introduce is theoretical yield, percent yield, and excess versus limiting. Yes, yes. So our goals for today, describe a method for determining which of the two reactants is a limiting reactant. And by limiting, that's going to be the one that kind of controls the reaction. If we, the more we start off with that, the longer the reaction can go. Once it's used up, the reaction stops. So we'll calculate the limiting reactant. We'll calculate the amount of moles or mass in grams of a product given the amounts of moles and masses. So that's, again, gram to gram, mole to mole. And we can do it with two reactants when one of them is in excess. Distinguish between theoretical yield, actual yield, and percentage yield. And percent yield is going to be a comparison between theoretical and actual. And then we will calculate percentage yield given the actual yield and the quantity of the reactant. So we have kind of dealt with percent yield already to a degree back when we were doing empirical molecular, all of that. We're just going to take a different perspective on it with this, and it's based on reactions. The other side of this, I am looking to test the stoichiometry on Wednesday, but that's really going to depend on how we do today. If I see that we're getting it and we can move forward, then the test will be Wednesday. If we're not getting it, then tomorrow and Wednesday will be kind of review stuff where we're just practicing this material, and then Thursday will be the test. So I really need to see where you are at. That's why I want to collect PS3 so I can go ahead and grade that and see where the mistakes are. Because I'll learn a lot from that to be able to know how far we can go. I'm going to kind of flip my agenda in the order that I teach this. I'm going to teach the percent yield material first, and then come back to the limiting and excess. As the percent yield is a little bit easier calculation to do. So go ahead, take a few more minutes. I want you to finish up PS3 if you have not done so already. If you are finished PS3, you need to be working on the PS4 sheet and go from there. Yes. I can print one out. Yes. So let's go ahead and look at this and see how we do this. So what would be the first thing that I need to do on this problem? All right. So first step, I need to check for balancing. So is my equation balanced? How can I start fixing it? All right. So what would I need to do to boron to get it to be balanced? I need a coefficient of 2 on this side. All right. So when I do that for oxygen is 3. How do I fix oxygen over here? Coefficient of 3. Now, what does that make me have to do to my magnesium? I need a coefficient of 3. All right. So when we're looking at this equation, the question is how many moles of boron can be obtained from 10,000 grams of dibromine trioxide. That was a tongue twister. All right, so starting this, what am I? What formula am I using? What stoichiometry equation am I using? I'm going grams to moles, mass to mole. All right, gram to mole. All right, so what's the first thing that I'm going to put on the left? (10,000 grams) B2O3. Now, I know that there is a tendency to not want to write the formulas for these and all of that, but it's a good idea to show the chemical formula for each thing. It's a good idea to show the units for each thing and not get lazy on this, at least until we get good at these, so that we know what's going on. All right, so what's my second step here? After I've done 10,000 grams of B2O3, what do I need to know? All right, so I'm going to put 1 mole on top, and this is 1 mole of B2O3. What am I trying to accomplish right here? Going from grams to mole. So what goes down here? 1122 plus 32. This is 44. Yes, I did boron, which is 10.8. I rounded it to 11. And oxygen is 16. So actually, that's not the right number. Sorry, it's 70, right? All right. So at this point, does everybody understand where I got 70 grams from? Anybody not get it? We have 2 bromines, or 2 borons, sorry, at 10.8 each, or 11. So 11 plus 11 is 22. Then we have oxygen that is at 16 each, so plus 16 3 times gives us 70. All right, now, so we have went from grams to mole of diboron trioxide. What is my next step? All right, what do we call this step? Mole what? Mole ratio. And where does our ratio come from? What do we call this thing right here? Balanced equation. So my mole ratio comes from the balanced equation. I'm going from B2O3 to what? Boron. All right, so I have how many moles of this? So it's 1 mole of that. That comes from the fact that I have a coefficient of 1 there, to 2 moles of boron, and then that should be, yes. Because my question is asking for boron right here. How many moles of boron? All right. So you should be able to solve for that one. All right, going for part B. Part B says how many grams of magnesium are required to produce 4,000 grams of boron. So this one is going gram to gram. All right. Now we're given a new set of information here. We're not worried about A in this particular context. So we're going to look at just the new set of information. So we have 4,000 grams of boron. I need to go from grams to moles. So there is 11 grams boron for every 1 mole boron. I need my mole ratio. So what is my mole ratio on this one? Oh, wait. Yeah, 3 moles of magnesium, sorry. All right. So I have 3 moles of magnesium for every 2 mole of boron. And then what would be my next step? I'm in moles. What do I need my answer to be in? Grams. So what number am I going to put here? Molar mass of magnesium, which is 24 over 1 mole. All right. So go ahead. Now that you have the setup, go ahead, try to do these real quick. All right, verify your answer. I got 285.7 moles of boron. Did anybody get anything different or not see how I got that? So doing this one, you're going to take 10,000 divided by 70, and that'll give you moles of diboron trioxide times 2, because we have 2 over 1, and that should give us 285. So 10,000 divided by 70 times 2. On this one, we're going to go 4,000 divided by 1 over 11, or divided by 11, times 3 halves, or times 3 divided by 2, whichever way you want to look at that, times 24. And this is going to be a fairly large number, but we should end up with 13,090 grams of magnesium. All right, any questions? All right, so we have when we are solving any stoichiometric equation, when we're solving any stoichiometric problem, we are determining what's called the theoretical yield. Basically, what we're saying is if we did an experiment where we took X grams of this material, we want to know theoretically how many grams we can produce or how many moles we can produce. That would be if everything in the lab went exactly perfect, that you had 100% of what you put in come out. But we know that in a real world situation, you never get 100% efficiency. So we get what's called, so when we do the stoichiometry, we get what's called the theoretical yield. The answer that we come up when we apply any of those equations is theoretical. That's what we think we're going to get, or that's the maximum amount we can get. The actual yield is what happens in the lab. So theoretical is mathematical. Actual is application in the lab. That's what we produce. So real world actual should never be as much as our theoretical. Actual should always be a little bit lower. And so we get this concept called percent yield, and it's a ratio. It's a ratio of the actual to the theoretical. So we take the actual number, divide it by the theoretical, multiply by 100, and it gives us the percent yield. How close were we to the expected amount? All right. So it's kind of like a percent error calculation, but we don't have to. We're not seeing how far we off. We're just seeing how much of the expected did we get. And I'm just verifying something in the text real quick to make sure. Yeah. So it's actual divided by theoretical multiplied by 100 gives us the percent yield. Now, a lot of times we're going to use this in conjunction with limiting and excess, where you would do the limiting and excess first and determine the limiting to get your theoretical, and then you come into this. But I want to teach you this part first because it's easier, and then we'll go back to limiting and excess. And I'm going to try to show you a shortcut for limiting and excess when we do it, so that you don't have to do as much. All right. So let me grab this color. So theoretical . All right, so theoretical yield, again, is the answer determined by a stoichiometric calculation. Actual yield results produced in the lab. All right, and percent yield is the comparison between the two. Does anybody need more time on this? You know, if you turned your phone sideways when you do that, you'd get a better picture. All right. So moving on. All right. So let's look at this sample problem. I'm going to let you, I just lost my connection. All right. So we have this material called chlorobenzene. It's used in the production of many important chemicals such as aspirin, dyes, and disinfectants. One industrial method of preparing chlorobenzene is to react benzene with chlorine as represented by the following equation. So benzene C6H6 in liquid form plus chlorine gas reacts to form chlorobenzene and hydrochloric acid. Hydrochloric gas, hydrogen chloride gas. When if we react 38.6 grams of benzene with an excess of chlorine, this should be Cl2, not that should be a subscript 2, not a full size 2. When we react 36.8 grams of benzene with an excess of chlorine. So this is one of those words that you need to pay attention to. When we see this in the equation, when we see this word excess, what is that telling us? For the main thing is we tell them we have more than what we need, that there's going to be a bunch of this left over. We don't need to know how much is there. We just know that we have more than enough. So what's going to be important is this number here, which is telling us that our benzene is our limiting reactant. This is the one that's controlling the reaction in this particular case. So we're going to look at this, and first thing I need to do is what? What is my first step to begin this equation? I need to make sure it's balanced. So I have 6 carbons and I have 6 carbons. I have 6 hydrogens and I have 5 hydrogens here plus 1 hydrogen there. It gives me 6. I have 2 chlorines and I have 2 chlorines. So yes, it is balanced. Now, before we can calculate the percent yield, we need to know a couple of things. Well, we know that this 38.8 is our actual yield. What we want to know is what could we have theoretically produced? How much chlorobenzene could we have produced theoretically? So I need to take this number, 36.8 grams. So I'm starting in grams, and I want to get to grams. I want to know how many grams of chlorobenzene could I produce. So I'm going grams to grams. So what's the first thing I need to do? I need to divide it by its molar mass. So I have 1 mole C6H6. And what is my molar mass of benzene? 78. Yep, 78. All right. Now, what's my next step? Going from benzene, so I have 1 mole of benzene, C6H6, and I'm going to chlorobenzene, C6H5Cl. It's a 1-to-1 ratio. So again, this step in this particular one is not necessary, but I want to show it just so that I know what I'm doing. And then I need to go back from mole to grams. So I need to know the molar mass of chlorobenzene. And then that'll give me my answer. So this is theoretical yield at this point. So what number should I put here? What is my molar mass of chlorobenzene? Say again. 113.45. I got 112. It kind of depends on how you round it. I'm going to go with 113 just as a whole number, especially dealing with what I'm dealing with. All right, so how many grams of chlorobenzene can we produce? Okay, sorry. So theoretically, we can produce 53.3 grams C6H5Cl. All right. So theoretically, we could produce 53 grams. What in our lab, how much did we actually produce? $38.8. So what is my formula for percent yield again? So it's actual over theoretical times 100. So when I set this up, it's going to be 38.8 is my actual over 53.3 is my theoretical times 100. So what is my percent yield on this one? 73%. So that means that in the lab, I'm only 73% efficient. Most of the time in our labs, we are going to come out somewhere around 50% efficient. So you're never going to be 100%. The closer you are to 100%, the better your lab was, the better your process was. You want to try to get as little error in this as possible. You want to get the maximum yield that you can, because that produces less waste. So the lower the waste that we have, the better off we are. So let's go ahead and talk about limiting and excess. Wow. Yes. All right. So don't worry about the diagram down here. I'll talk about this, but I don't want you to draw it. What we do need to know is the definitions of limiting and excess. So a limiting reactant is the reactant that limits all right. So limiting reactant is the reactant that limits the amount produced. This is the one that's going to drive the chemical reaction. The excess reactant is the substance that is not used up. So looking at the diagram down at the bottom, we have 5 carbon atoms and we have 10 oxygen atoms. And so we're looking at a reaction that's going to be carbon and oxygen combined to form carbon dioxide. Well, carbon dioxide is CO2. So it's going to be 1 carbon for every 2 oxygens. We have 10 oxygen molecules here, so how many oxygen atoms do we actually have? 10 sets of 2, so we have 20 oxygen atoms, and we only had 5 oxygen atoms there. So to make what the maximum number of carbon dioxide molecules that we can make, since we only have 5 carbons, we can only make a maximum of 5 CO2 molecules, and that ends up giving us 5 extra oxygen molecules that are in excess. So in this one, the carbon is the limiting, oxygen is in excess, and so we're able to produce that carbon dioxide. Yes, ma'am. This can happen in any type of reaction. This happens to be a combustion. So we're combusting carbon. Well, even that, you're going to have a limiting and an excess. So if I'm combining, trying to think of one that I can do without it being combustion. Let's say we're making hydrochloric acid. We have hydrogen, we have chlorine, H2 plus Cl2. We have 10 Cl2 molecules, and we only have 5 hydrogen molecules. Well, when it works out, it goes 1-to-1 to each other. So the maximum that we can make is 10 HCl molecules because we started off, we had 5 H2s, which means we had 10 hydrogens available. So it's kind of like if you want to build a tricycle, you need 3 wheels, 1 frame, and 2 pedals. So if you have 6 wheels, 2 frames, and 3 pedals, how many complete tricycles can you make? 1. We need 1 more pedal to complete that tricycle. All right, and that's all this is. It's just how many can we make from what's there, and we're going to have some extra left over. All right. So let's look at a practice with this. Can everybody read that, or do I need to make it larger? I'll make it larger. Not that big. A little bit more. Let me type some. If I do that, it's going to be real small at the top. All right. So this one is an example of a limiting reaction problem. We want to be able to determine how much, which one of these is the limiting. So in these, let's start it off. Silicon dioxide, which is also known as quart, is quite unreactive but reacts readily with hydrogen fluoride or hydrofluoric acid according to the following reaction. Silicon dioxide plus 4 hydrogen fluorides yields silicon fluoride plus H2O. All right. So looking at this prompt right here, if 6 moles of hydrogen fluoride are added to 4.5 moles of silicon dioxide, which is the limiting reactant? How is this question, how is this prompt different from the ones that we've previously seen? Okay, so if anytime you see a problem that has 2 givens, always means that we're looking for a limiting reactant. All right, now, so it always means that we're looking for a limiting reactant. A lot of times the question won't just stop there. It won't say which is the limiting reactant. It'll say what is the theoretical yield of this. So in order to find out the theoretical yield of this, we need to find out which one is the limiting, because that's going to tell us the maximum that we can produce. It's going to be a smaller amount than the one from the excess. So whichever of the two produces the smallest amount is our limiting. So let's go ahead and look at how we would set this up. So one of the things I want us to realize is we have two reactants. We have reactant A and we have reactant B. So we're going to have two different problems that we set up here. Where is... There it is. So, ooh. So let's go ahead and set this up. So problem A, what am I going to start off with? Now, that's the other thing to look at. What is my information given to me in here? Moles. So all we really need to do is go moles to moles. It doesn't ask us, all it's asking us is which is our limiting. It doesn't tell us that we're looking for grams or anything like that. If it doesn't ask for it, you don't have to do the extra work. So we're going to do the simplest process. It's mole to mole. So the first step, we're going to do reactant A, which is hydrogen fluoride. So we have 6 mole of HF is reacting to produce, and we're looking at what we want to produce silicon fluoride. So we're going to go from hydrogen fluoride, which is 4 HF, to 1 mole SiF4. I mean, I guess we could there too, but we're really trying to get it really doesn't matter which of the products that we choose. I chose silicon fluoride because that's the main product that we're making. Water is a common substance, so I'm not real worried about production of water. Silicon fluoride would be the one that we're trying to get out of this, that we want to use. We can do it both ways just to see, but so for now, so we have to do this, and then setting up reactant B. It's done much the same way. Reactant B, we're going to take 4.5 moles of SiO2. And then we set up our mole ratio. Now on this, whichever one of the products we pick, we want to stick with the same product in the in this. So we have 1 mole to 1 mole And the limiting is going to be whichever one is the smaller amount of the two. Did I do that right? No, I didn't. Sorry. I typed it in wrong. 6 divided by 4. Sorry, 1.5. And then this is 4.5 mole. So which one is our limiting? A. This is our limiting reactant. All right. And this is our excess. All right. So this is our limiting, this is our excess. And then another question I could ask you on this is how much of the excess would be left over? How do we find that out? That's right. So we're going to take, we started off with 4.5 moles of silicon dioxide. We're going to subtract 1.5 silicon fluoride from it, and that tells us the leftover. So that will tell us how much excess we had left over. So it's going to be, what's that, 3? So we would have 3 moles of silicon dioxide left over at the end of this reaction. All right. So this is what I want us to do. You should have had 2 other sheets that you grabbed today. I want you to spend time practicing